So, in this session we will be referring to several kinds of numerical problems, and we will try to solve them. We have already covered many aspects of reliability modeling, and we have considered 5 typical problems related to all these aspects of reliability modeling, and we will be discussing these numerical problems one by one. Okay. So, similar such problems you can expect for your the home assignments. Okay. Later on we will give you the home assignments, and so first you must go through these typical numerical problems. So, I am going to discuss 5 typical problems related to reliability modeling. Now, let us talk about the first problem, the time to failure density function. Okay. We have already referred to what is the time to failure density function in respect of reliability modeling. Is it okay? That means this density function must be known first, and for knowing this density function you need to collect data. Is it okay? So, later on we will referring to the kind of data you are supposed to collect for concluding on say time to failure density function. So, time to failure density function for a system, we have already defined the system, is given by Ft equals to 0.005, okay, 0 and t varies between 0 and 75 days. It's fine. Determine RT, the hazard rate function, the MTTF, mean time to failure, the standard deviation, the median time to failure. So, how do you solve it? That means that RT is equals to T2 up to 75. That means 75 days it must last, it must survive. Is it okay? So, that is Ft dt, T2 75, 0.005 dt. So, this is a constant. So, 75 minus t, t 75 minus t. So, that is 375 minus 0.005 t. So, this is the expressions for RT. It's clear. So, when the t varies between 0 and 75 hours, is it okay? So, this is the first one. Then what is the lambda t? Lambda t, if you recollect, that lambda t is the failure rate function is Ft, that is the probability density function divided by RT, that is the reliability function. So, 0.005 divided by, now RT already derived this expression 0.375 minus 0.005 t, when t lies between 0 and 75. I think it is very clear. Now, how do you compute mean time to failure? Again 0 to 75, that is it must survive up to 75 hours, RT dt. Is it okay? That means this is basically the mean value you calculate. So, that particular formula you use, and the RT expressions already we have derived, that is 0.375 minus 0.005 t into dt. Is it okay? So, now you go for integration and you get a value of 14.0265. It's clear. So, this is that means the mean time to failure is just greater than 14 days. Is it okay? And what is the variance? Variance, again you apply this formula T square Ft dt minus MTTF square. Is it okay? Like say mu square we use in fact in general formula. So, ultimately you follow these steps and you say that the sigma square is, that is the variance, 505.37, and obviously the standard deviation is 22.48 days. Is it clear? So, that is standard deviation as well as the variance. Now what is the medium time to failure? Again we apply this formula, that means 1 minus 0.005 T median. So T median is already given, that is the T median is to be calculated, and this is 0.5, is right. And so what is the T median? That means median time to failure, that is 100 days. It's clear. So this is a typical say an example of the numerical problem, and we have derived the corresponding the expressions already. Is it okay? Now second problem is is also a typical one, like given RT, this expression is given e to the power minus root over 0.002 t. Okay, root over t is greater than 0. Calculate the reliability for a 100-hour mission. Is it okay? That means what is the probability that it will run for 100 hours? Is it okay? Or it will survive for 100 hours? What is the hazard rate? Is the hazard rate increasing or decreasing? Is it okay? We have already explained that what is its implication. If the hazard rate increases, what does it mean? And if the hazard rate decreases, what does it mean? Whether under what conditions or what are the possible reasons of hazard rate increasing, or what are the possible reasons that the hazard rate is decreasing. If the burn-in period, we have already explained what is this burn-in period. That means this is also referred to as early failure phase, or you can say that the child mortality phase. So if the burn-in period is 15 hours, find the reliability for a 75-hour mission. Is it okay? Calculate the design life for a reliability of 0.96 given a 15-hour burn-in. Is it okay? So, so these are the four the questions we have set. Now we need a solution. So against question number 1, what is the answer? Answer is that the reliability that it will run for 100 hours is e to the power minus root over 0.002 into t. So the t is 100. So you get a value of e to the power minus 0.6687. That means it is 0.1512. That means probability is just greater than 50%. It is considered to be very, very less. That means you may conclude that this reliability is poor. It may not be acceptable. So that interpretation you also must have. Is it okay? You must be, whenever you get some result, you try to interpret the value or the result from the reliability perspectives. What is lambda t? First you calculate lambda t. d dt of E. Is it okay? So that means it is root over 0.002 t. That's why it is written as minus 0.002 t to the power half. Okay. And lambda t is essentially ft by RT. So RT is already given, and ft is essentially ddt of capital FT. Is it okay? So so this is half. So ultimately you apply this formula. Is it okay? And you get the expressions like this. That means lambda t is given by 0.001 root over divided by root over 0.002 t. Is it okay? So you follow these steps, and definitely I'm sure that you will be able to calculate this value. Is it okay? So you just follow the steps, or you just try to get these expressions independently without looking at these steps. From the above expressions for say lambda t, we can see that that it goes to 0 as t goes to infinity, hence it is decreasing. Is it okay? So so the t is in the denominator. So if the t increases, obviously the lambda t decreases. Is it okay? So failure rate is decreasing over the time period. Okay. So that is your observation. So that is your interpretation, right? Now this is the expression that is the conditional in the reliability. So R, so reliability, the T plus TO plus T, provided that it has survived for T0 time period. Is it okay? So what is T0? That means it is the burning in phase. Is it okay? So what is the burning time? That is the 15 hours. So it has already survived. That means for 15 hours it has survived, it has not failed, and then only it reaches in the useful life period. And what you are trying to conclude, that means 75 hours in the useful life phase. So the total timing is 75 plus 15. Is it okay? So that means it is 90 hours or the 90 days, whatever may be the unit of measurement. And then you apply the formula, assuming that the constant failure rate. So this is the timing is 15, okay, and this the timing is 90. So just you have this value 1.1891 in the numerator and 1.5285 in the denominator. So you get a value of 0.778. Is it clear? So your reliability is just it's approximately 0.78 or 78%. Is it okay? Coming down, coming to the next question, that means the 15, the T time period, T plus 15. So this 15 hours actually is spent in burn-in phase. Is it okay? That means early failure phase, 15 hours. So again you apply this formula. So this becomes 0.96. So ultimately, the value of T you try to determine. That means you want to increase the value of the reliability to 0.96. So obviously, how long, for which time period this is applicable. So what you find that this is just with 7.91 hours. Okay, 7.91 hours. That means you have just you have come out from the burn-in phase. Now you are in the useful life phase. That means the component is in useful life phase, and the failure rate is increasing at a very fast rate, and that's why when you just start working for, or say you are running the systems or running the component for just 7.9 hours up to that the time period, the reliability is 0.96, and as you start using this component for continuously for the time period during the useful life phase, you will find that there will be a sharp decrease in the reliability value. So that is your observations, that is your interpretations. Okay. So what you might conclude that this is not acceptable, as far as this component is not acceptable as far as its reliability is concerned. So such sort of conclusions you are required to make when you carry out such analysis. Okay. Now let us discuss the next problem, problem 3. The time to failure in years for a system, again we are referring to a system, is given by Ft is this. Is it okay? 400 divided by T plus 14 to the power 3 for T equals to greater than 0. Is it okay? Find the reliability for the first year of operation, calculate the MTTF, determine the design life for a reliability of 0.96, comment on the failure rate. Is it okay? Many a time you have to do that. Comment means you have to interpret the value of the failure rate. Compute a 1-year burn-in period and comment on the failure rate. Is it okay? So these are the 5 the questions you have, and then what you have actually, the RT is given by T to infinity Ft dt, that is 400, okay, T to infinity, right, T dash plus 14 to the power minus 3 dt, okay, this formulations you have, and ultimately when you compute these values, okay, you follow these steps, you get an expressions like this 200 RT divided by t plus 14 to the power 2. Is it okay? The square terms. That means it is the function of t, and the t is in the denominator. Is it okay? That means if t increases, obviously the reliability decreases. Is it okay? So that's a relationship. Now, if the t is just 1 year, what happens that you get the value of reliability for 1 year, and this is 0.889. Is it okay? So it's so 0.889 is the reliability value. Is it okay? Now, so the next part is you are computing MTTF. Is it okay? Again, we apply this formula. Is it okay? You have these expressions 200 divided by t plus 14 square into dt. You just carry out this these computations, and ultimately you get the value of 14.2857 years. So that is on an average. Is it okay? The mean value of the time to failure. Is it okay? And then we go to the next part, that is the reliability. This is the expression, that is 0.96. So what will be the corresponding the time period? So t is 0.4337 years. Is it okay? So you just apply this formula, and RT value is specified, that is 0.96. Is it okay? So this way you compute the value of t. Okay, you just follow the steps. And the last one, the next one is, that is the failure rate function, that is Ft divided by RT. That is the basic equations you have, the basic expressions we have already derived in the previous lecture sessions. You have derived this expression. So you refer to this particular expression, and then you know what is the value, what is the expression for Ft given by this expression, and similarly RT already you have computed. So ultimately you get a value of 2 divided by t plus 14. So therefore, when lambda 0 is equals to 0.2 and lambda t to the power t tends to infinity, it becomes 0. Is it okay? Hence the failure rate is decreasing. That means decreasing failure rate case. Is it okay? Now this is so with this is a failure rate, so it may not be acceptable to you. Now you have to think of ways and means to improve the reliability. Is it okay? That means what are the ways in which at least you can make the failure rate, is it okay, constant? Is it okay? So if you can do that, that means many a time you opt for the technical solutions. You need to many a time you need to change the technology. Many a time you need to change the materials. Is it okay? Or in certain cases you need to change the configuration of the system if you are dealing with the system's reliability. Okay, so these are the options. Now the last related to the fifth questions, we have this one. Is it okay? That means it has already survived 1 year. What is the probability that it will survive for 2 more years? Is it okay? So this is the expressions, and you apply that formula, and what is this reliability? That reliability is 0.879. okay, a 1 year burn-in period, that is this 1 year burn-in period. Okay, you have successfully overcome all the problems that you might face during the burn-in phase, and then the component starts working in the useful life phase. Is it okay? So 1 year burn-in period is over, and obviously this will improve the reliability because the failure rate is decreasing. Is it okay? Failure rate is decreasing, right? So 0.879. So if you really during the burn-in phase, you might face several kinds of problems. Is it okay? And when you face these kinds of problems, you have an in-depth understanding of the design features. and obviously you try to improve the design. Is it okay? So such exercises you do routinely, and it is expected that when the burn-in period is over, that means the quality of the product has improved, the design of the product or the component has improved, and that's why you may assume that that the failure rate has come down to its minimum level, and then this failure rate with its reduced level will continue during the entire the life period, or say the useful life period of the product. Okay, so this is your interpretation. Then we move to the next problem. The reliability of a mechanical component is a component wise, is not a system. So the reliability of a mechanical component is given as this, another expressions. You may raise a questions. So sir, how do you get this expression? Okay, later on we'll discuss this part, that how do you get these expressions, right? So there is a method you apply to get these expressions. It's in empirical form. Is it okay? So here, what is the expressions for reliability? That is RT is equals to 1 minus T upon 2 T0 square. The whole expression is square it. And the value of T, the maximum value of T is T0. Is it okay? So this is the condition where T0 is the maximum life of the mechanical component. It's clear? Find out whether this mechanical component is experiencing wear out. That is very important. That means now we are referring to the third phase. So what is the third phase? Third phase is wear out phase. Is it okay? Now what you need to conclude, that whether the component is in the wear out phase or not. Is it okay? During wear out phase, what is why do you say you are in the wear out phase? Because during the wear out phase, the failure rate increases, okay, at a very high rate. So from this analysis, when you carry out analysis, when you try to solve this problem, whether you will get an expressions for the failure rate, and you conclude that the failure rate is increasing at a very high rate, and then only you say that possibly in all likelihood the component is experiencing wear out. Is it okay? Calculate the MTTF, mean time to failure. Is it okay? Obviously, if it is in wear out phase, what do you expect? That the mean time to failure will be very, very less. Is it okay? If suppose during the useful life period, suppose the mean time to failure is around say 20 hours, in all likelihood, if the component is in wear out phase, the mean time to failure could be significantly less than 20 hours. That means it could be as low as 3 hours, 4 hours, 1 hours. That means constantly you are facing a failure event, and then you are seriously thinking whether I will continue with this product or not, or I will just withdraw the component. Okay, I will ask for a replacement of the component at least. Is it okay? Find the design life for a reliability of 0.95. It is pre-specified if the maximum life of the component is given as 3000 operating hours. Is it okay? So this is another dimension of the problem. So wear out is indicated by increasing failure rate. I have already pointed out this one. So lambda t is, this is the basic expressions you have. Is it okay? That means this is Ft by Rt. Is it okay? Ft by Rt. Now you have this expression already, it is given, Rt expression is given. So here you have these Rt expressions. Here you have minus ddt of Rt. This is ddt of Rt. So ultimately you follow these steps, you simplify, and you get this expression, that is 1 upon T0 minus T by 2. Is it okay? Now lambda 0 is 1 upon T0. That means when lambda 0 you have 1 upon T0, and lambda T tends to T0. Is it okay? That is increasing failure rate. So it is increasing failure rate, right? So MTTF, that means you have proved that you are in the your failure rate is increasing, and that's why in all likelihood the component is in wear out phase. Is it okay? So that is your conclusions. Now the next part is that is how to compute MTTF with the given problem. Again you use the same formula. So that is RT dt, say integration 0 to T0, and then again you compute this one because RT is known. You follow all these steps. Is it okay? And you get these expressions in terms of T0. Is it okay? That means 7 upon 12 T0. Okay. So this is the expressions for MTTF. Okay. So if the T0, that means that is the maximum value. Is it okay? It lasts up to T0. So at T0, what is your MTTF? That you can always calculate. Is it all right? Now, what is the expression for reliability? That is these expressions of the 3000 hours, working hours. The reliability is 0.95. So now you calculate that what is the time period. So you just get from these expressions you get the time period. The time period is 151.9234 hours. Is it okay? So this is just straight you apply this formula to get the answers. Now we will be referring to the next problem, that is problem 5. Determine the following for a component experiencing chance failures. What is this chance failure? That means it is when that means the chance failure phase or useful life phase. Is it okay? That means when the the failure rate is assumed to be constant. So the component experiencing chance failures, that means there is randomness. It might fail, but there is no as such there is no assignable causes. There are some because of some natural causes it is failing. Is it okay? And these natural causes do exist in the system. So chance failure phase with an MTTF of 1200 hours. Suppose the MTTF value, mean time to failure, is specified, and that is around 1200 hours is a point estimate. Reliability for you need to determine reliability for a 300-hour mission. Design life for 0.92 reliability. The median time to failure. The reliability for a 300-hour mission when the second redundant component is added. So that is the problem number D. So we will be answering the first question, that is reliability RT e to the power minus lambda t is a chance failure phase, that means useful life phase. So we assume that exponential time to failure, that means the constant failure rate. So e to the power, that means t upon 1 upon MTTF. Why you have used to 1 upon MTTF? Because lambda is 1 upon T or MTTF. Is it okay, lambda? So this is the expressions for RT. So when T is 200 hours, you get a value of reliability as 0.8465 or 84.65%. Now this is reliability for TD. So again you apply this formula, that is e to the power minus TD divided by 1200, that is 0.92, and this is already specified. Okay, you refer to the question. So what is the value of TD? TD is 100.06 hours. Is it okay? Next, we use this formula for determining the reliability with medium time. That means it will last for the medium time. What is the reliability? That means e to the power minus T median divided by 1200, that is 0.5. Already it is known 0.5. So T median, the way we define the median time to failure, okay, so that reliability is 0.5. So corresponding hours is is 831.77 hours. And this one is RT is 1 minus probability that both components fail. Is it okay? Is referred to the part D of the problem. So how do you express the reliability, that is 1 minus probability that both components fail simultaneously. So for each one this is 1 minus RIT. Is it okay? So this is the failure probability. Obviously, so it is 1 minus the reliability. Then both the components we are using, that means this into this, that means 1 minus RIT to this square. And so for RIT expressions you have e to the power minus t upon 1200. So these expressions already you have derived, and since the components are identical, so what you say that if the value of t is 300, so corresponding reliability is, that is R 300 is 0.9193. That means here you use a value of 300. Okay, so this problem is also a typical problem. So these 5 problems we have discussed today and in this session, and similar such problems will be discussing in the subsequent lecture sessions. Okay, and we will be referring to not only reliability related problems, as reliability is closely linked with the quality. So there will be few sessions, as lecture sessions, exclusively on the numerical problems. So where we will be solving problems on both reliability as well as on quality, because the till date we have covered a large number of issues related to the quality control as well as the reliability modeling. So there must be certain sessions where I will be discussing a set of numerical problems. Okay, so right.